Hi everyone. A small note. So the idea was to have this presentation in English because the Grand Master Plan is to have at least one presentation per time slot in English. Is everyone fine with that? Yeah, perfect? Great. But I'm obviously Ukrainian, so please do feel free to ask me questions in any language you're comfortable with, except maybe Klingon. I'm not fluent in Klingon. Okay, today I want to tell you, clicker, how we manage load in our data centers. And to begin with, I want to give you a bit of context about the work I do. I work in a company called Cloudflare. Cloudflare is a reverse proxy technology. We stand in between client request and your services exposed to internet. It can be, for instance, like our majority of clients are HTTP websites, HTTPS, but we can protect any port you like. We provide content delivery services. We have caching services, unlimited DDoS mitigation. We make some website optimizations. We implemented support of TLS 1.3. We are working on implementing Quick. We have support of server push, MP, and so far. We also are the fastest managed DNS provider in the world. We have not only authoritative DNS, but also a resolver, which we launched in April this year, 1.1.1.1, or that terrible IPv6 address. We also do DNS security. We serve more web traffic than Twitter, Amazon, Apple, Instagram, Bing, and Wikipedia combined. Anytime we push code, it immediately affects 200 million web surfers, and every day more than 10,000 customers sign up for our services. We have 152 data centers in 74 countries. We serve more than 10 million domains. We serve 10% of all internet requests. 7 million requests per second on average. Almost 3 billion people served each month. The biggest DDoS attacks we have ever seen was 942 gigabits. And the biggest DDoS attack in history was 1.5 terabits. And we have 15 terabits of network capacity and growing. This is the map of our data centers. All of these points are our edge data centers. We have core data centers and we have edge data centers. Core data centers store like databases, logs, and all of this stuff. And edge data centers do actual content serving. Life of a packet. Long time ago, there was ARPANET, which could fit on one A4 datasheet. This is the scheme of peering between data centers in 1973. And there is such a project called OptE. They visually map peering between internet service providers. And the last time they did that mapping was 3 years ago, and this is how it looked like. So it's very highly connected. Load balancing between data centers. First of all, DNS. Obviously, we can return different A records or AA records based on some locality logic or congestion control logic, different proprietary algorithms, and so on. All of this is exposed via Bgp Protocol. And then, in our case, we use anycast routing. Bgp Protocol is also called a protocol of two napkins, because in 1989, the draft of this protocol was like drawn in this napkin. I found it interesting. Types of routing. So there is unicast routing and there is anycast routing. Unicast routing explicitly says which IP address belongs to which server, while anycast exposes a number of metals servers using the same address. So we use anycast routing both in between our data centers and inside our data center. Okay, let's go inside data center. A typical data center looks like this. So we have internet, we have core router, we have rack of servers, and we have a top of rack switch. Top of rack switches, they can be connected differently, but the idea remains the same. So, problems with load balancing within data centers. First, uneven load. we want our servers to be equally loaded. So we would pay the same amount of money for resource usage for every single metal. Another problem, different kinds of traffic. We have to support different protocols. Another, some protocols like DNS, it makes sense to do per packet load balancing for them. Another one, it's very painful for us, heterogeneous hardware. We have 9 hardware generations, and if I'm not mistaken, like 4 of them are in use. So different kinds of processors, different kind of network cards, different routers, different switches, like whole zoo. Another problem, for instance, for cache, it makes sense to check for locality. We want to make the same requests appear on the same servers. And transport affinity, we obviously don't want to break any connections and make the same packets appear on the same metals every time a request per session comes in our data center. DDoS. For some companies, DDoS is not such a big problem, either because they're small and they don't care, they use like intermediate providers to fix it, or they control the source of traffic. But in our case, we do not control which traffic comes in, and we highly distrust this traffic. Group change. For instance, if one of the metals in the data center goes up or down, we have to support transport affinity. So still, packets within one session would come to the same metals. Another one, from numbering, sorry. Graceful connection draining. We want to be able to control our metals. For instance, we want to do some maintenance of a metal. So we want to gracefully draw connections. Say, like this server, you are going to stay online for 10 extra minutes. So continue serving requests that you already were processing, sessions that you were already processing, but please close WebSockets, and please do not accept any new connections. There are a few techniques to achieve that. The first one, and very obvious one, equal cost multipass. It's a router technology, so it's supported by routers. It basically computes ID of a packet and makes modulo n where n is an amount of metals in your data center. ID is usually 3-tuple or 5-tuple for TCP, source destination IP, source destination port, and protocol. But there are a few problems with that. The first one, uneven load. So we have SMP groups where you say that if you calculate this hash, then, and this is the first time you do it, this packet should go to metal from this group. But the problem is we have different generations of metals in the same group. So different CPU capacity. We obviously can do kind of static load balancing and, for instance, add unicast addresses of like more powerful metal multiple times. But still, it's static load balancing. We do not check for actual load in our servers. Another one, different kinds of traffic. Do we care whether it's TCP, UDP, or quick traffic? We don't. Per packet load balancing. No, we do not check which protocol we are using, which protocol this packet has. So we can't do per packet load balancing. It supports heterogeneous hardware. It supports transport affinity until we do not do group change. Because if metal goes up or down, the whole group is rehashed and our connections break. And it doesn't support graceful connection draining, because like, how can you tell that this server should be shut down in X minutes? You can't do that. There is equal cost multipass consistent hashing. It's basically the same, except for it supports ability to keep the connections until metal goes up, down. But it gets rehashed if metal goes up. So like 50-50. We do support partially group change. Obviously, there is stateful load balancing where you would be just saving which connection belongs to which metal, and it solves lots of problems like uneven distribution because it's like software-defined networking, and you can like check what is the actual load on this metal. But DDoS, if we are saving state, we are not DDoS resistant. We are going to be overflown, our connection tracking table will get overflown, and we're done. So there is Google Maglev implementation of load balancing. They introduced it a few years ago. However, it's not open sourced. They just published paper, did a few presentations how they do it, but like with no deep details. The idea is they have software-defined networking, but this daemon works in user space, so they use kernel bypass. What I do like personally, and why I added this to the slides, is that Maglev introduces their hashing for transport affinity, which is reused, it's open sourced, and it's reused by many similar technologies. Daisy chaining. Beginning of this year, if I'm not mistaken, a Romanian university, scientists from Romanian university, they introduced their stateless load balancing, where they do not keep per connection state. Instead, what they do, they use a kernel module, so they use a hugs kernel, and they expose kernel's connection tracking table and reuse this information and benefit of switching from connection tracking to sync cookies using Linux network stack. This is how it works. So basically, there is a packet, there is like choice of backend, it comes to the server. If this connection is present in connection tracking table, it remains on this server. If it's not, it gets forwarded to a server that is supposed to have this connection in connection tracking table. So new connections are always handled locally, and there is also timeout for requests, which allows to do graceful connection draining. So Beamer solves all of our problems. It can support uneven load. We can do per packet load balancing because we already hack into kernel. We already hack into network packets processing, so we can add this possibility. It supports DDoS mitigation. It would survive group change. But spoilers, performance could be even better. And there are links, so this solution is fully open sourced. You can take a look on it. Also, I must not forget to tell you about FPGA packet processing. If I'm not mistaken, because there isn't much information on commercial use of that, Microsoft uses it. They process packets on FPGAs. But obviously, there is such a problem as, like, you have to buy these FPGAs and install them in your data centers and support yet another type of metal. It's not good. Fun fact. An average IoT device gets infected with malware and launches an attack within 6 minutes of being exposed to the internet. Over the span of a day, an average of 400 login attempts per device, 66% of them on average are successful. Because, I mean, like, no one changes passwords, default passwords, especially in IoT. Over the span of a day, IoT devices are probed for vulnerabilities 800 times per hour. I'm scared, are you? There are 3 main types of attacks. Technical difficulty, you can see it, perfect. So there is volumetric attack, where basically you expose some protocol vulnerabilities. The most famous one is DNS. So you spoof IP address of a packet, you send DNS requests to resolve this domain, but response, DNS response, it can be way bigger than request. And the victim, DNS resolver victim, it sends the results of this request to a chosen spoofed IP address. It's still happening. It's, I think it's the most frequent type of attack. And recently, in February, there was an attack on memcache servers. There were using UDP vulnerability of memcached, and like lots of memcached instances on the internet happen to be not closed from the world. People are strange. So the amplification factor for memcached attack was 50,000. It's terrible. So one byte and you get 50,000. There is protocol attack. The most famous one is SYN flood, when you send SYN packets, but you never send, so server responds in ACK, but you never send ACK packet back, and server's connection to the tracking table gets overflown. And there is application level attack. So volumetric and protocol attacks, it's layer 3, layer 4 attacks. And application attack is layer 7 attack, where you when you use different vulnerabilities of applications. For instance, if some particular web pages goes like slow database queries, it's a vulnerability. Mitigation. In any team, you need a tank, a healer, a damage dealer, and someone with crowd control abilities, and another one who knows IP tables. It's so true, trust me. Because IP tables are everywhere. So a request comes from internet. It gets to your router. And then it comes to your NIC. And then IP tables, it's always IP tables. And only then application. And I want to do a short introduction into technology called BPF, Berkeley Packet Filter, or eBPF. It's Extended Berkeley Packet Filter. It's basically sandboxed bytecode running in kernel. It's always safe to run because kernel, before loading this code, it does verifier checks. It checks whether it's safe to do. And it's written in subsets of C, so it's easily programmable. It is present in Linux starting 3.15, so pretty old. And also Brendan Gregg likes it. If you don't know who Brendan Gregg is and you're into systems programming, I highly recommend this guy. He is absolutely awesome, and like the way he explains things, it's top notch. So you can use eBPF for debugging like literally anything in kernel. Classical BPF machine. It was like kind of, didn't have a lot of registers, was not flexible. So what's used nowadays is extended BPF machine. So it has more registers, it has stacks, and it has the most important thing, it has maps. It's data structures that are exposed both to kernel part and user space. So this is the way you exchange data from your user space daemon and kernel. And how we mitigate DDoS attacks. So on every single edge metal, we run a process called gatebot. We do packet sampling on this gatebot. So basically it sends some percentage of packets to our core data center, where we do aggregation and analysis. Then we detect malicious traffic. Then we compile rules which would mitigate this kind of traffic. And then we deploy it back using key value storage to our edge data centers. All of this takes like a few minutes to detect an attack and deploy mitigation. Initially, we used IP tables. That's why the joke. It was the only tool to filter traffic. We leverage such models as IP sets, hash limit, con limit. Then XT BPF module was introduced, and it allowed you to run this custom BPF code on IP tables stack. But soon, we started experiencing IRQ storms during big attacks, and all CPUs were dropping packets while user space applications were starving of CPU. Well. Then, obviously, we introduced kernel bypass. So it's when you send packets directly from your NIC to user space. Our kernel bypass is based on library from the major manufacturer of our NICs called SolarFlare. Network traffic is offloaded to user space. It also allows us to run BPF rules, and it's way faster than plain IP tables. But we get rid of one CPU because it should be busy polling NIC. And inserting packets back, if the traffic is not malicious, is very expensive. And the most painful point, it's hardware dependent. We can't use any other NICs. Terrible, terrible, terrible. How are we going to live? XDP to the rescue. I love this technology. So XDP, it's a novelty introduced in recent, I don't remember, sorry, which one kernel. But basically, it's kind of API introduced by kernel for network card drivers to hook onto this API and process packets on driver level. So not reaching Linux network stack, which is known to be slow. It can drop packets, it can transmit packets, and it can forward packets back to Linux network stack or to user space, like since 4.19. How we use it? Examples. So this is this subset of C code. Basically, you have a rule, you check for the return code of this rule, and you do something. Sorry. If rules don't match, you just pass this packet further to the stack. You can use multiple conditions in the rule. It depends on you. And you can do like extra calculations like login, metrics, or whatever you like. And you can use these magic maps to share information between kernel and user space. So as a result, we can drop 10 million packets per second using XDP. And major network card producers, they do implement XDP support. So like Solarflare, Mellanox, XGB, Virtuo.net, so you can run it on VMs. So it's very widely adopted. You would ask, what about DPDK? It basically does the same, but in user space. Instead, I would just quote you Alexey Starovoytov, one of the developers of XDP. So you don't need to allocate huge pages. Obviously, it requires way less resources. No special hardware requirements. You basically introduce API from Linux, and then it's up to driver developers to implement it. You don't need to define a new security model. Dedicated CPUs are not required. It's up to you how you deploy this, how you manage this stuff. So basically, our solution is XDP for both load balancing and DDoS mitigation. First, we mitigate DDoS attacks, and if it's not malicious traffic, then we choose our backend based on some health check information or CPU data, like capacity and so on, and then we pass it. So add to this daisy chaining, like that Beamer technology, and you get graceful connection raining. And this is the best performance-wise solution. You can't do any better. And they lived happily ever after. Bonus part. How many of you have heard of a protocol called QUIC? Oh, quite a few. That's nice. So we are working on implementing QUIC. QUIC is a protocol which is supposed to replace TCP and TLS level of application stuff. So it runs on top of UDP. And this is how a typical QUIC request. So in HTTP, you get TCP handshake, and then you get TLS handshake, if you use HTTPS, obviously. And then only you proceed to HTTP. But if you use QUIC, you get QUIC handshake, and that's it. You proceed to HTTP. It's way more performant. It's more flexible, but QUIC must support IP address migration. So every QUIC packet, once the connection gets established, it has a connection ID, and based on that connection ID, we have to support migration of IP addresses. So basically, if client's IP address changed, we shouldn't break connection. We should treat this session as already established. But this is a problem. I mean, like, you can't support it with ECMP or any other like stateful load balancers. All4LB. you must implement your own software-defined networking in order to support Quick, because obviously Quick is not supported by Linux kernel, is not supported by routers. It's basically like the standard is not finished yet. So, yeah, thank you very much. Do you have any questions? And also, sorry, please do feel free to ask questions in any language you like. So I'm perfectly fine with that.
Подскажите, пожалуйста, когда вы планируете открыть CDN-ку в Украине, потому как в данный момент пускать сайт сквозь вас — это откровенная боль в плане скорости.
Okay, do we have non-Russian Ukrainian speakers? We don't. We don't, okay. No, because in the beginning we did. Окей, у нас есть дата-центр в Киеве. Я не могу вам сказать, есть ли планы открывать дальше дата-центры, но мой personal hunch будет, что дата-центры будут расти, потому что трафик в Украине растет, и прежде всего благодаря введению 3G и обещанию 4G, то есть больше будет пользователей. А почему больно к нам подключаться, я немножко не поняла. То есть, ну, есть дата-центр в Киеве, да. Скорость загрузки падает. Давайте ваш конкретный пример я могу просто переадресовать людям, которые этим конкретно занимаются. Может быть, у нас просто бывает такое, что какие-то конкретные статические ресурсы, вот они как-то себя не так ведут. И каждый use case такой, который вы говорите, что замедляется скорость, он на самом деле уникальный, и его нужно дебажить уникально. Каждый конкретный кейс. Я с удовольствием вам дам мои контакты, пожалуйста, напишите мне, я переадресую людям, которые этим заинтересованы, мы с удовольствием вам ответим на все вопросы. Спасибо.
Спасибо за доклад. Есть вопрос, возможно, немножко не по теме глубокой технической части, но последнее время появляются все новые и новые виды атак. Там DNS amplification уже вроде как никого не удивишь, удивляют только новые масштабы. Но появляются ли какие-то кардинально новые сейчас виды атак, с которыми вам приходится работать и решать те проблемы, и вы не знаете, как их решить? То есть какие вот именно самые челленджевые сейчас проблемы?
Окей, ну виды атак, они все равно не меняются, все равно основное количество это синфлуды. Но в сентябре прошлого года мы introduced, я извиняюсь, иногда очень тяжело слова, ввели, да, спасибо. Вот, мы ввели unmetered mitigation для DDoS, то есть даже наши бесплатные клиенты, они получают unmetered mitigation DDoS атак. И наша статистика показывает, что как только мы это ввели, у нас количество атак уменьшилось, потому что стало просто неинтересно. То есть 15 терабит, ну, будет очень тяжело забить 15 терабит, и так, чтобы и мы этого не поняли, просто тяжело. Новые виды атак, то есть все те же, вот последний был такой вот новый, это атака на memcached, но опять же это был amplification атака на Bgp Protocol. То есть все то же самое, просто новый application, который администраторы этого application забыли закрыть. Вот. А application layer атаки, их очень мало, они на самом деле небольшие, потому что их очень тяжело делать. Нет, мы защищаем. Вопрос был, защищаем ли мы от атак application уровня. Мы защищаем от атак application уровня. Мы используем челленджи, мы используем CAPTCHA, мы используем Web Application Firewall. И еще одно преимущество, то что у нас 10 миллионов клиентов, и если кого-то атакуют, и мы находим какой-то паттерн в этом, как атаковали, делаем какие-то выводы, то мы вот эти вот знания мы деплоим как бы на всех оставшиеся 10 миллионов минус 1.
Ну, в реальности я этого не заметил. Когда приходится бороться с DDoS, то как раз через Web Application Firewall, наверное, берешь и банишь те адреса, которые тебе прилетают, которые ты на своем уровне детектишь как абьюзер, и тогда через вас закрываешь, чтобы разгрузить себя уже свои ресурсы. Но вот чтобы вы конкретно могли отловить application level, я даже не представляю, как вы можете это нормально сделать. Когда у тебя трафик похож на легитимный.
Да, но в этом и проблема. То есть application level атаки очень тяжело сделать, но и тяжело отловить. То есть как бы we are doing our best, и мы постоянно работаем над продуктами, которые бы вот это вот как-то улучшили. Но опять же, если вот есть какой-то конкретный use case, что вот сказать, что вы не отловили вот эту атаку, хотя вот она очевидна, то есть, пожалуйста, пишите нам, мы только за, мы очень любим фидбэк, и мы только за improvement. И чем больше мы фидбэка получим от наших клиентов, тем... Боже, я звучу как sales. Я инженер, я не sales. Вот, то есть чем больше мы фидбэка получим, тем больше у нас будет информации, на базе которой мы можем строить там наши модели и применять их конкретно вот на наших edge дата-центрах и митигейтить атаки. Спасибо.
А у меня есть еще тоже вопрос. А как близко вы к разработке Quick? Интересно, вы Quick делаете себе или каким-то продуктом, который потом можно опенсорснуть будет? Вообще вопрос, наверное, скорее, вы будете его опенсорсить или нет?
Я, честно, не знаю ответа на вопрос, будем ли мы опенсорсить, но мы над ним работаем, и мы не скрываем, что мы над ним работаем, но детальные планы, ну, даже если бы я знала, я бы, наверное, не сказала. Но stay tuned, у нас скоро Birthday Week, следующая неделя у нас Crypto Week, мы будем объявлять новые крипто-штуки, не криптокарренси, а криптография. Вот. А после этого у нас будет Birthday Week, где мы будем представлять новые плюшки.
Елена, а можно ли чуть подробнее, что происходит с одним из случайно отобранных пакетов, которые попадают в Core Data Center, чтобы решить, это фрод или не фрод, и создать правила?
Мы не рассматриваем пакет как один пакет, потому что если один malicious пакет, ну зачем нам париться и тратить на него вычислительные ресурсы, правильно? Мы берем пачку пакетов какого-то размера и смотрим их паттерны. Если мы видим какой-то четкий паттерн, ну вот, например, IP-адрес — это нехороший паттерн, потому что он очень легко спуфится, но тем не менее практически после каждой атаки мы строим карту происхождения IP-source адрес, чтобы посмотреть, в принципе, ну хотя бы на что спуфят, может там это что-то скажет. То есть мы обрабатываем их пачками всегда.
К тому, что там это machine learning или какие-то эвристики, или там какой-то lookalike, что это в принципе?
Мы используем machine learning для этого в том числе. Мы используем machine learning для атак 7-го уровня. И мы используем просто эвристические алгоритмы для атак 3-4 уровня, потому что plain packet, в общем-то.
Спасибо.
Спасибо.